Hi everyone. Hi everyone. This is Dr. Vishal Sharma from the Carrier Ethernet Group, back again with another one of our network design and architecture series briefs that I'm doing here this week. And as I mentioned in one of the earlier ones, the objective of these briefs is to take a discussion from the Carrier Ethernet Group that has been extensively talked about and pertains to a network design or architecture problem that a lot of the practitioners are either facing or going to face in the industry. And somebody brought the question up and we had a good discussion on it, and then it's time to kind of wrap it up and bring the distilled version out to the group and to the community at large. And I've already explained in one of the previous videos sort of the objective of doing that. Let me quickly briefly recap what is the purpose of doing it. So in a sense, the reason of to do this, something like this is that when a discussion happens with something like 20 to 40 or 50 comments, it becomes very difficult for a new person coming in, or even some of the people that have been involved in those discussions, to even figure out what are all the different topics that were touched in the course of that exchange. So the purpose of this brief is to take out the very essence, or distill out the very essence of those discussions, and to consolidate and put things in context to help people appreciate the design principles that emerged from that discussion, and then to enable them to quickly summarize those and incorporate them in their own sort of practice, whether they are network designers, whether they're network architects, they are system designers, product management people, either on the vendor side or the operator side. So this particular, sort of the general flow of these hangouts, and I'm going to emphasize that at least till we get to a point where we've done enough of these that all of you know exactly what is going to be coming, is the following. So I tend to tell you what discussion or issue it is that we are focusing on. Then I'll show you where and how to find that discussion, because that's one of the key things. Where do you go to the LinkedIn group to find it? I'll give you some background on the subject and where to find that background, usually that relates to industry standards documents or industry literature that is helpful to set the pace for the discussion, help you to better understand it. And then we'll talk about, then we'll do a deep dive into all of the discussion that happened, talk about the key issues that were discussed, and then some of the highlights. And then we'll close up by giving you, if there are relevant standards documents that are useful for studying these issues, talk about the key conclusions that came out of this, and maybe hint at some open issues, and then some next steps, which is how you can contribute, how you can sort of be involved in expanding this state of knowledge. Now, let me quickly do a screen share with you and show you the specific discussion that I'm going to focus on right now. And that's best demonstrated using the mind map that we've been using so far for all of our videos. And you've all kind of seen that from the last couple of weeks. There you go. So let me position this a little bit better. All righty. So I'm focusing right now on this specific discussion call, which came from Eric Tim of TDS Telecom, who asked, is there a standard for configuring committed burst size in a device or in the network? And I think his question came from a number of the RFIs that they were seeing, where operators or service providers had asked for certain parameters and certain benchmark numbers of CBS. And so the way you'll find this discussion in the LinkedIn group is that I'm going to attach this clickable mind map as an attachment under the video. And when you click on it, it'll open up in a web browser, the standard web browser, and you can then navigate through it. And right like I'm clicking now, you can right click on this little LinkedIn icon. It shows you the location of the discussion. When you right click and you select open outside of Mind Manager, in your case, you'll select open outside of your browser. A new browser window will open up with the actual discussion. Something like, which I'm not going to show you here, but that's what it's going to be. Actually, what I'll do is let me quickly switch over to the actual discussion so you have a sense of what that looks like. And I'm going to have to navigate my windows here. And there we go. Alrighty, so that's the actual discussion. This is what it looks like. CBS standard has the MEF defined or published a standard for OVC, EVC, CBS. This is the question that Eric asked. And then there were a number of people that contributed to it. Larry Sandberg, of course, was a big contributor. I'm going to talk a lot about some of the examples Larry gave. There was myself talking about it. Ish Khan was there. And I think they were the three of us: Eric, Larry, Ish Khan. Raghu came up. It's provided from Sienna some excellent inputs on how to think about this problem and why some of the confusions that you'll soon see are prevalent in the industry come about. And so this is the place to go for the discussion, which is by clicking on the mind map. And let me go back to the mind map because I want you to see some of the references that are actually very valuable to looking at what we're going to talk about. Or maybe better yet, now that I've shown you where to find the discussion, let me start by telling you what we're actually going to be discussing in this analysis brief. So this is under our network design and architecture series, as I said earlier. And what we're going to talk about in this brief is we'll talk about whether there are industry standards for CBS, and then we'll have some general observations regarding CBS, which were discussed on the discussion. Very interesting observations regarding TCP/IP in relation to policing and metering and how that gets impacted, how TCP throughput gets impacted with a policer with CBS and the relationship there. I'll tell you a little bit about that. Then we talk about the usefulness and validity of the current vendor recommendations for CBS. So we have recommendations from Juniper, Cisco, Alcatel-Lucent, and Brocade, and the like. And it's useful to look at sort of where those recommendations come from, why they kind of make sense, given some of the things we know about how the network behaves, a TCP-rich network behaves. And then we'll give you some counterexamples and some discussions to illustrate that you have to be careful in how you use those recommendations and understand philosophically where they come from, because blindly applying them is not always going to work. And we'll show you some very simple examples where you can end up with a lot of problems. And we'll talk about why CBS has been thought about in a lot of operator RFIs in relation to CIR, even though you'll see that it's not CIR that CBS actually directly relates to. And we'll talk about some confusions that happen in the industry because policers and shapers are talked about and thought about in very similar terms. So a terminology that was actually designed to be used with shapers ends up also being used for policers. And then we end up with some contradictory situations where CBS and CIR kind of get directly related. And then I'll talk about some next steps, some interesting simulations being done by Steve Haddock on behalf of the MEF, an interesting white paper that I think the MEF is contemplating on the topic, and some open questions. So let me go back to the mind map for a quick minute. Or actually, no. Let me now dive right into the meat of the matter. So essentially, what is committed burst size? Well, if you can imagine a very simple policer which has a bucket. The bucket is filled at a certain rate, which happens to be the committed information rate, or CIR. And the bucket has a certain size B, often denoted by the committed burst size, which we abbreviate to be CBS. So that's pretty much how a meter or a policer is structured. Now, as packets come in from the source, the policer checks if there's enough tokens in the bucket to allow a certain volume of data to be transmitted on the outgoing link. It does that. The tokens are subtracted from the bucket. And of course, as the bucket is filled at the rate of CIR, new tokens keep getting added. So at any given point in time upon the arrival of a packet, if there are enough tokens to let the packet through, the packet is marked green and put on the output link. And if there are not enough tokens, the packet is actually marked red. And then there's an option. You can either drop it or you can let it go through the network, but with the understanding that at the first sign of trouble or congestion, it's the red packets that are actually going to be removed from the network. Obviously, you don't want the red guys to be creating problems inside the network. So that's pretty much what CBS is. So if you think about it, as long as you have a CBS's worth of data in the bucket, of tokens in the bucket, if you get a burst of data, you can transmit as much data as the amount of tokens that you have. And you can transmit that at line rate. So that's another thing I need to point out. The data is always sent at line rate because you have to transmit full packets. You push them out on the actual outgoing link at line rates. But data arrives at whatever bursty rate it does. And it's the CIR which kind of controls the rate at which green packets trickle through the policer. So if you work out the numbers, you'll see that on average, the rate at which traffic actually leaves the source and enters the line over a period of time is going to be less than or equal to CIR, with some boundary conditions accounting for bursts at the start of a long period of silence and so on. So another way to think about it, and I think Larry Sandberg likes to say that, and I really like this analogy, is that CBS is essentially a license to transmit at the full line rate for a certain period of time. And the amount of time at which you can transmit at line rate is decided by how big of a CBS you have. So if CBS is, let's say, 500 megabytes, and just for doing round numbers, your line rate is 100 megabytes per second, you know that you can transmit at line rates for 500 megabytes divided by 100 megabytes per second for 5 seconds. So that's the duration of time for which you have a license at the source to burst and send 500 megabytes of data into the network. So that's the first thing that we need to understand. And now the question is, are there any industry standards for CBS? And the answer is actually no. There are really no, at least MEF standards specifically for CBS. So then the question is, what general rules or observations can we make about CBS? And there are some interesting things that came up in this discussion that I think are worth summarizing here. So the first thing to observe is that unlike what you might see in a lot of literature out in the industry, CBS is not directly related to the CIR or the committed information rate, but rather it's really related more intuitively to the ratio of CIR to line rate. And that's easy to understand, because if CIR, let's say, is very close to line rate, if CIR is equal to line rate, if you're sending at full line rate, well, obviously you cannot have any burst because there's no room to burst. So CBS will be 0. If your CIR is very close to the line rate, you'll have a small CBS because there's only so much you can burst before you already start hitting the line rate limits. So the smaller your CIR is relative to the line rate, the higher your CBS can be because there's more opportunity for the source to burst. So that's the first thing. It's the ratio of CIR to line rate that really controls how big of a CBS you can realistically have. The second thing is, if you have very well-behaved traffic, let's say you have CBR traffic, constant bitrate traffic, then you basically have a very low CBS. In the ideal case, you'll have basically no CBS because the traffic is always transmitting at a fixed rate. There's just no variation in the traffic. And it's also important to know that CBS is related to maximum frame size. So it's typically set to be, it would be some multiple of the maximum frame size. If you're using the standard 1522-bit Ethernet frame, it'll be some multiple of that. If you're using the jumbo frames, let's say roughly 9600 bytes, then the CBS will be a multiple of that line rate. Now, the other thing is that having a large CBS doesn't actually come for free. I mean, there's always a cost, all right? We know there are no free lunches. So in this particular case, what happens is that if you have a large CBS, you build up queues and you have large latencies in the network. And you can have points, choke points, or at choke points or important aggregation points in the network, you can have large accumulation of data in the buffers. And that's something that you have to account for. So you cannot sort of willy-nilly set a large CBS at the ingress to the network and then hope that there's going to be no consequence further down the line as you go a few hops deeper into the network core. There will, in fact, be at some point an accumulation of traffic, bursty traffic at certain choke points in the network that will either have to be buffered, and if you're unable to buffer it, as we'll show in an example later on, you're going to end up having dropping essentially green traffic, which is not a good thing to be doing. And the other important thing we want to understand is that TCP/IP has interactions with policers and therefore is affected by the CBS. And what has been empirically found here is that TCP/IP, when it is fed direct, TCP/IP traffic is directly policed by a policer, it turns out that TCP/IP's throughput is typically a lot below the committed information rate unless you make a very large committed burst size. And intuitively, the reason for that is that when you have a policer, it can basically chop the TCP/IP bursty traffic and allowing the maximum burst that it can allow is a burst of size CBS, as I explained earlier in the video. So, but if your bandwidth delay product is considerably larger than the committed burst size, then what you can imagine is that TCP/IP is sending a small amount of data at a point, limited by the policer equal to the burst size, but it's not really filling up the pipe, which is the amount of data it can send equal to the bandwidth delay product. And if you know your TCP/IP theory, you'll know that TCP/IP is most efficient and has the maximum throughput when it's filling up the pipe fully. So when it's transmitting at a rate which keeps the pipe full equal to the bandwidth delay product. But if you have a policer in the path and you're cutting it off at CBS, then obviously if CBS is much smaller than the bandwidth delay product, you're going to have a very low TCP throughput. It's going to interpret all of that traffic as a loss, and it's going to go back into slow start phase again and again, and the average throughput will be low. So therefore comes the rule that if you want to have good performance with TCP/IP traffic in a police network, you have to set the CBS of the order of the bandwidth delay product, which can be pretty high to get good TCP throughput. Otherwise, the other option is that you police the output of the source. I'm sorry, you shape the output of the source so that there's no burstiness in the traffic. It's well-behaved traffic, and you feed that into the policer. And if your shaper at the source and the policer at the ingress of them, so let's say the Metro Ethernet network, are matched, you're going to get good TCP throughput because there's going to be no burstiness that's going to cause the policer to cut TCP off at a certain level of traffic. So let me talk about, quickly do a screen share with you again and show you some references that I've put together for you in the mind map and what they talk about. And you're going to find that of value, I think. Let me see if I can get my screen share button here. Alrighty, let's go back to the mind map. Let me share with everyone. Sometimes I forget to do that. And we're back to this discussion, the CBS discussion. So what I've done here is I've provided you some nice references to understand more about CBS and throughput. And I think, let me give you a quick reference to a few of them. One is a very nice document from the MEF, a white paper that talks about carrier Ethernet throughput, and that's linked directly from here. The other is RFC 6349, which is a framework for TCP throughput testing. Even though we're not talking directly about TCP here, but as you've seen, there is interactions between TCPs and policers, and the committed burst size has a role to play. So it's useful to look at this RFC if you like. At least I want you to be aware of it, which describes how to do TCP throughput testing more extensively than has been the case so far. And you'll find some good material there. The other reference that you'll find in here is an XF4 document that talks about testing as per RFC 6349. And that has some nice diagrams and figures in there. In particular, towards the latter half of the document, you will see them giving you some examples of how they isolate the causes of poor throughput. And once they determine that it's not the buffer and it's not the network, they figure out that it's the policer that's causing TCP to get truncated and causing poor TCP throughput. So you'll see that in that document. And then finally, we have pointers to examples of vendor recommendations for CBS, which I have given you pointers to Alcatel-Lucent's policies, Cisco's recommendations, Juniper's calculations of burst size, and some documents from both Brocade. And I'll talk about these in a minute. But just so you know that all of them are there, and there are some observations I had, a couple of them, which are in the comments. And when you click on the comments, you'll actually be able to see what text I've put in there. So that's about where to find the background information on the subject. Let's now go back and talk a little bit more about the vendor recommendations and how valid they are, or under what circumstances they're valid. So the vendors have, as you might imagine, provided some guidelines about how to configure CBS in their specific routers and switches. And I want to quickly go over the recommendations of the 4 key vendors. So Cisco, if you look at the references I provided, suggests that the committed burst size be calculated as follows. They say, well, you take the CIR, or the committed information rate, divide by 8 to get a rate, convert from bits per second to bytes per second, and then you multiply by about 1.5 seconds. So it's CIR divided by 8 times 1.5. And they've discovered that in testing TCP traffic, they've discovered that the burst values should be several seconds worth of TCP transmission at the average rate, or the CIR rate. So from there comes this recommendation that the CBS should be 1.5 times CIR divided by 8. And that's kind of a rule of thumb that you'll find in Cisco documentation related to iOS. If you go to the Juniper documentation, there are 2 ways they propose to set CBS. One is with a logic similar to Cisco's. They say, well, it can be some multiple of CIR, and that multiple varies between 1 and 600 milliseconds, with the sweet recommended spot being about 5 milliseconds. But it can go as high as 600 milliseconds. And later on in the video, we'll show you that when it goes to 600 milliseconds, you can get into some trouble. On the other hand, Alcatel has a slightly different way of recommending CBS size. The reason is that they recommend CBS as a fraction of the buffer space on the line card of the Alcatel 7750X devices, which is where the documentation refers to. And if you look at through the calculations, you'll see that their numbers work out to between 1 and 2 kilobytes on the low end to about 4 megabytes at the high end with their, and so that's their range. And similarly, if you go to the Brocade documentation, they reference 5 jumbo frames as the minimum CBS size, which if you do the calculations works out to roughly about 40 kilobytes. And their max for a particular output link or an interface is 750 megabits per second, which again, if you translate into our standard megabytes number, you'll see that it comes out to roughly 93.75 or 94 megabytes of CBS size. So that's the 4 vendors sort of recommendations. Now the question is, how useful and valid are these recommendations? And why did the vendors come up with these? Now, based on what I told you earlier, that the TCP performance becomes very poor when you have a policer in the path, and the only way to actually get good performance is to have a high CBS. So therefore, you'll see. I'm sorry, and one thing I need to go back to is that the other recommendation from Juniper is that if you don't want to sort of do it as a fractional line rate, you can make it some multiple, typically 10 packet sizes of the maximum transmission unit, the MTU. So that's kind of the trade-off. Now, the vendor recommendations are high, probably because they are trying to find a trade-off between choosing a not too large CBS, but at the same time helping the operator pick a CBS that's going to be large enough to get good TCP throughput. But as we'll show you in a moment, there are cases, very simple ones of simple access devices, where if you just followed these rules to the letter, they would lead to unreasonable delays or unreasonable losses, or both. So that's some of the problems. So let me now show you guys some calculations that I've done, and you're just going to see my handwritten calculations here because I wanted to get this out to you in quick time. And so I'm going to just show you my calculations, which have been borrowed from Larry Sandberg. So just to illustrate that, if you just use some of these rules that the vendors have provided, I'm just going to look at the rules of the 2 largest vendors, Cisco and Juniper, and see what numbers they give us. So at small CIRs of like 5 megabits per second, 10 megabits per second, maybe the numbers are not that large. But let's say you get to 500 megabits per second, as I'm showing you here. If I use Cisco's formula, CBS is CIR divided by 8 times 1.5 seconds. You plug in the numbers, do the arithmetic, and you come up with 93.75 megabytes, or almost 100 megabytes. Now, clearly, that's a huge buffer size for a single flow or a single interface in the network. If you use Juniper's formula and you take the maximum high end of their range, which is 600 milliseconds, you can arrive potentially at 37.5 megabytes, which is also a very, very large buffer. And what these kind of large buffers do is that they influence your network design and the traffic engineering of the network. Quite obviously, because if you have to put these large buffers, for one thing, you're going to have very large buffers. 2, you're going to have huge delays for the amount of time it takes to clear these buffers at line rate. And to illustrate that example, I'm going to go into the second part of my calculations and show you how that works out. So let me just lengthen this so we can see the entire page in one shot. So what I'm doing here is I'm assuming that the CBS is the equivalent of 15 milliseconds. So that what that means really is that the CBS buffer empties out at a line rate C, empties out at line rate C, whatever C might be, in 15 milliseconds. So the buffer is 15 milliseconds times C in size. That's one way to look at it. So let's look at 2 cases. Let's assume that the committed information rate is half of the line rate. So it's C by 2. So then in the time 15 milliseconds that the bucket empties out, we would have, again, you remember there's a tap filling tokens into the bucket at the rate of CIR. So we would have filled an additional C by 2 times 15 milliseconds worth of tokens into the bucket. So if there was data to send, the source could transmit for how long? C by 2 times 15 divided by 1 over C, because the data would be transmitted at line rate. which is 7.5 milliseconds. So in the time that it takes to empty the CBS bucket of tokens at line rate C, that is the 15 milliseconds, 7.5 milliseconds worth of tokens have arrived again. And so the source could burst again at full line rate for another 7.5 milliseconds. And you would get, you could have a burst potentially of 22.5 milliseconds. Now, obviously, as you can see, this can go recursively. I'm not going to go through multiple levels of recursion, but I'm just trying to show you here that you can burst for at least 22.5 milliseconds if your line rate C is, your CIR is half of line rate. Now, if CIR jumps to 80% of the line rate, which is 4/5 of C, then in the 15 milliseconds that it takes for us to empty the bucket at the line rate C, we receive how much additional data? 4/5 of C times 15 milliseconds, which is 12 C worth of tokens into the bucket. Now, if the source was going to potentially burst, it could burst at and give so much data that is equivalent to emptying 12 C worth of tokens at the line rate C. And so if you divide out by, I'm sorry, there's a typo here. This should have been C, not 12 in the denominator. You would get 12 milliseconds of transmission time. So the source effectively would be transmitting first for 15 milliseconds, emptying out the bucket of tokens. And then in the time that the bucket was emptied, you would have filled in another 7.5 milliseconds worth of tokens that can allow the source to burst at line rate for 12 milliseconds. And you would get a total of 27 milliseconds. So in this case, it could burst for 27 milliseconds. And as you can see, the closer the CIR comes to the line rate, this number increases exponentially until it asymptotically goes to infinity, which means that if you are transmitting completely at line rate and your CIR is line rate, quite obviously you'll never empty the bucket and you'll never have to fill it. It'll just remain filled all the time, and you would be able to transmit at line rate C indefinitely. So that tells us that if you choose buffer sizes based on the configured parameters by the vendors, that can be a somewhat problematic exercise because you have very large buffer spaces. And let's talk a bit about how that can be problematic. So let me take you through the second of my examples, which again, thanks to Larry here, and walk you through the calculations to show you what exactly happens. So what we have here is we are assuming a simple 24 by 1G switch. We have 24 access links, each running at 1 gigabits per second, and one 10 gig uplink as shown here. And let's assume that each of the access links, we have a uni feeding it with a CIR of 100 megabits per second. All right. And for calculating CBS, we just use the Cisco formula per each input uni, which is 100 megabits per second divided by 8 times 1.5. That's roughly 8.75 megabytes. And if you add up a little bit of overhead because of CIR being able to burst, let's round it off to about 20 megabytes. Now, if all 24 of these access links, the unis were going to burst, the sources were going to burst, you would potentially have 20 megabytes times 24 or 480 megabytes of data because your CBS was set to 20 megabytes if we actually did that. Now, that means that we have 480 megabytes of data arriving simultaneously on the switch. Now, how much time would that be? This would arrive in the time that it takes for a 20 megabyte bucket to be emptied at 100 megabits per second. I'm sorry, at 1 gigabits per second, which will work out to be 0.16 seconds. This is a typo here. I should have divided by the line rate C, which is 1,000 megabits per second divided by 8. And that will give you 0.16 seconds. So in this much time, how much of this 480 megabytes can we actually send through the uplink? Well, the uplink transmits in this much time at what rate? It transmits at 10 gigabits per second, which is 10 times 10 to the power 3 megabits per second, times 1.6 divided by 8 to make everything into bytes. You work out the numbers, and it's going to transmit to 200 megabytes in that 0.16 seconds. So that means that we got 480 megabytes in. We transmitted 200 megabytes in the same amount of time on the uplink. We have a net balance of 480 minus 200, which is 280 megabytes of data, all of which was, by the way, marked green because it all cleared its CBS police and buckets, and that the switch is technically obligated to deliver. Now, there are very few access switches that would have that kind of buffering in the switch, and especially for one given interface. So that's the first problem. So let's assume that there are no buffers in the switch that can accommodate this kind of data, which means that potentially 280 megabytes of green or whatever, the buffer size minus 280 megabytes minus the max buffer size in the switch, that much amount of green data is going to be potentially dropped by the switch, which is a very unhappy situation. If that was not the case, and we really said, all right, fine, let's assume that these buffers exist in the switch, how much time does it take to clear that amount of data? So to empty this 280 megabytes at 10 gigs per second, you go through the calculations, you need about 224 milliseconds. So what that means is that the last packet that is sitting at the end of this 280 megabytes is going to have to wait for over 200 milliseconds just on one single hop. Now that's, for those of you who know about voice latencies and VoIP and so on, will realize that the voice budgets are typically, this is the entire end-to-end voice budget for a voice or VoIP session. So we have two problems. Either the provider drops traffic, which is also very odd because the input links are barely 10% oversubscribed, and the output link is only 25% oversubscribed because it's 100 megabits per second times 24, which is only 2.4 gigabits per second on a 10 gig link. Just to remind you, this is the output links, and this 2400 Mbps uni is feeding that. So we've only got 25% occupancy here. We have only 10% occupancy here. So even at the maximum, at 25% occupancy, the provider, if they don't have enough buffering in the switch, is going to have to drop green traffic. Alternatively, they're going to have to face huge delays for some packets that are unfortunate enough to sit at the end of the buffer. So obviously, that's not something we want. And the purpose of illustrating this counterexample was to show you that you cannot really take the vendor recommendations just on face value. You have to kind of think about network architecture and design, which brings me right back full circle to the title of this series. So then the question comes that, Eric, if you go to the thread, you'll see that Eric shared a small extract of an RFI that he was looking at. In fact, let me actually do that for you right now. Why not? Let's look at what Eric showed us. And you'll see that the RFIs from the operators, and here's the extract that Eric put right here. Do you support a committed burst size to account for short-term microbursts? Carrier X requires a burst size of the following values. So you'll see here that the burst size kind of increases as the CIR increases. And based on what we just discussed, that's actually counterintuitive, because as CIR increases, you're actually going to need to burst less and less, and there's less room for you to burst. So equating burst size to CIR isn't really the thing we should be doing. We should really be sizing up our burst size based on how long we are willing to let a source burst at line rate, and how much of aggregated queuing we're willing to have happen at intermediate choke points in the network. And of course, those are not hard and fast numbers. That's where the experience and the skills of the network architect and the network designer come into the picture, because when they're sizing the network, they would have had to take these canonical numbers into account. And when they sign SLAs with certain customers, you have to again take these numbers into account so that you can provide right expectations in your SLAs. And the reason this happens is because, as I've told you, all of the vendor recommendations relate CIR directly to CBS. And they do that in an attempt to kind of get around the poor TCP performance issue, which, if you're an operator, maybe you've seen that already. You've got customers that are complaining that their traffic is showing very low throughput. And if you have a policer in your network, it's probably a good idea to put a Wireshark or something equivalent in there and check how much of TCP traffic you're getting at the uni, and how much of that is actually showing up at the remote end. So that's this is why operator RFIs even today seem to have questions that relate the CBS to CIR, that kind of explores that mystery. Now, another very interesting thing that Raghunathan of Sienna pointed out to us was that we have to look at how shapers are defined. And in fact, in the documentation that I referred to you from Cisco, you will see that in the very same page, in their policing and shaping overview, they talk first about policing and then the very next breath about shaping. And what Raghu pointed out was that in many cases for a shaper, you define the shaper based on 3 parameters. the burst that the shaper can tolerate, a time interval TC over which the shaper can receive the burst, and the rate at which the shaper transmits traffic on the output link. So for a shaper, if you look at the average rate at which traffic leaves the shaper, it's basically given by committed burst size CBS divided by TC, the time interval over which you can burst. And so CIR for the shaper output is CBS by TC. Now, the same output from the shaper becomes the input to the policer at sort of the remote end of that link, coming into the SEN or the MEN. And so very often that gets translated also into the policer CIR CBS, and you have the relationship that CIR and CBS are directly proportional. But you got to remember that the origination is more from the shaper side, and it's primarily because we are viewing them as mirrors. We just kind of tend to slap the same thing on the policer parameters, even though that's not entirely accurate. So that's not really what we should be doing. It's kind of a mistake to relate the shaper parameters as is to policer parameters. All right. So, but there's good news, as Larry pointed out in the discussions, and if you read it, you'll see that there is Steve Haddock at the MEF who's been running a lot of simulations for TCP/IP traffic, and there is some empirical evidence now to show the fact that if you shape TCP/IP and then direct it into a policer, you get very good performance, and if you don't, you need a very, very large CBS, typically of the order of the bandwidth delay product, and typically of the order of several megabytes, several tens of megabytes, which is what most of the vendors, excluding Alcatel, recommend. So what are the next steps then? The next steps are to wait for more results and more discussions, hopefully from the MEF, on these TCP/IP simulations. I hear from Larry and some of the other MEF experts that there's probably a white paper in the works that's going to describe the results that Steve has gotten. And there's still some open questions on CBS. So let me, in closing, summarize what we learned about CBS. And there's about 13 different things that we learned. So going back full circle, and thanks to Eric Tim of TDS for putting this together. And one is that there is in fact no MEF or industry standard for CBS so far. What we have are vendor recommendations, but I've already explained to you that you have to be careful when you look at those. The CBS is a size, not a rate, which we kind of know, but in many of the documentations, you'll see that it's often expressed in megabits per second. I'm sorry, megabits per second, even though it should really be a number in either megabits or megabytes. And many service providers are requesting CBS using rate values like CIR, and we need to be careful when we look at those numbers. Many of them are relating CBS as being directly proportional to CIR, which also we need to be careful of. It kind of works if you apply the vendor recommendations, but as I showed you in the counter examples, that's not what may be feasible in real life. And even though CBS is married to CIR values, it might be a better option to calculate CBS based on a service provider's MTU size, whether they're using ordinary frames or jumbo frames. And while it's not a standard, one of the possibilities for computing CBS is to have a CBS which is more than 10 times the maximum frame size, and the recommended number could be 10 or higher. Now at about 100 or so, you get into large buffer sizes, so maybe it needs to be a little bit less than that, maybe between 10 and 50, something like that. Now, if the traffic is well behaved, then the CIR over line rate is high. The ratio, if either the traffic is well behaved, it's CBR, or if the CIR over line rate is high, it's a ratio close to 1. You don't really need a high CBS because you cannot burst in that case. And if you use the proportionality formula, it would tell you that you need higher and higher CBS, whereas the reality is the reverse. And if you set a very large CBS in the tens of megabytes, that obviously has a cost, which we saw in the 24 gig switch example. And what it leads to a very large quick queue buildup due to many users bursting together, which means you have impractical queue sizes. Or you can have very large delays, as we saw in a couple of hundred milliseconds for a packet that's unlucky enough to be stuck at the back of that queue. And the other thing is that the empirical evidence has shown that it's better to shape TCP traffic before directing it into a police network, because otherwise what has been found is that the CIR and the actual TCP throughput are very far apart. Throughput is much lower than CIR, and that's typically because of a small CBS, TCP traffic bursts can get truncated as a result of which, the TCP will think this is a loss. It's going to go back into a quick start and slow start mode, and the average throughput is going to be very low. So the only way to overcome that is either shape TCP or put a very large CBS of the order of the bandwidth delay product. And the vendor guidelines, even though they may appear contradictory, are really trying to find a balance between recommending a CBS that makes sense and can account for the known poor TCP performance in the face of policers, vis-a-vis a CBS that is not set so high that it gives you unreasonably high buffer numbers. So there's some trade-off involved there. But nonetheless, we still have several open questions. One is, who among you are actually using these vendor recommended CBS formulas to configure CBS? And if you are, what kind of performance are you getting in your network? Or have you had to adjust them based on practical experience that you might have gathered? And if you haven't done that so far, but you intend to, then probably you want to at least look at some of the issues that were highlighted in this document. And the other issue is, what happens, how actually should we set CBS? Should we just set it as a small multiple of the maximum frame size because we don't know better? Should we look for some guidelines? Should we look for simulation results that may be coming out from the MEF that'll give us some guidance? And if so far you don't have any guidance, how have you been setting your CBS? And how has that worked out for you? We'd love to hear that. You can either come and join us at a subsequent hangout, comment on the discussion, start a new discussion if this is a related topic that you want to talk about. All of them is fair game. And finally, this is a question that Eric asked, which is, how does CBS vary between the mobile backhaul carriers and the Ethernet providers? Is it that the mobile backhaul carriers have more stringent requirements, and therefore we need to worry about their network and their CBS? And that's something that's an open question. Some thoughts have been shared on the network, but really we have no definitive conclusions at this point. So we'd love to hear your views. I encourage you to share that. I encourage you to let us know how we can do better on this network design analysis series that we are on, and what other topics are worthwhile covering. If there's something that you saw in the LinkedIn group or even elsewhere that you think is important enough to talk about, drop me a line. I'll be glad to look at it and maybe invite you over to frame the problem for us, share some of your experiences so that others can benefit from that, and we build this little library of best practices that all of us in the industry can then use to make ourselves better practitioners and to build more robust carrier Ethernet and packet networking designs. So thanks very much for watching. Until next time, may the bits in your bytes and the bytes in your brackets be profitable. I'll see you next time.